So we are slightly ahead of the schedule now, which is interesting and uh, useful. I think we can close early. So this is the awards session. So we have a couple of awards, Best Paper Awards and the SMART-101 Challenge Award. The Best Paper Awards were selected from the awards that were submitted, the papers that were submitted, and some of the papers were selected for oral presentations, which you saw today. And out of those oral presentations, we selected 3 papers for Best Paper Awards. And these Best Paper Awards are sponsored by Math Kangaroo USA. The first Best Paper honorable mention goes to this paper, Uni-NLX, Unifying Textual Explanations for Vision Language Tasks, by Fawaz Samani and Nikos Deligianis. Please, if you are around, please come over to collect the award. Yeah, of course. Have one more honorable mention, which goes to the paper Iterative Robust Visual Grounding with Masked Reference-Based Center Point Supervision by Menkao Li, Chunle Wong, Wenquang Feng, Shuchang Liu, Wang Liang Cheng. I don't know whether I'm pronouncing it correctly. Bear with me. Shantai Li, Bingkao Liu, and Chi Cao. Is there anyone around to collect our? Yeah. And the Best Paper Award goes to the paper Self-Graph PQA, a self-supervised graph neural network for scene-based question answering. And it goes to Bruno Cesar de Oliveira Zusa, Marius Asan, Helio Petrini, and Aaron Remariz Rivera. Bruno, please come over to take the award. Please speak up. And these, like I said, these awards sponsored by Math Kangaroo. And now we have the Smart 101 Challenge Award. You might have already seen. So Smart 101 Challenge is essentially a set of puzzles which second graders can solve easily. For example, these are the puzzles sample puzzles from the data set that we have shared publicly. And so there are different categories of puzzles, like algebra category, counting, path tracing, and other categories like arithmetic and such. There are 8 different categories. And usually these problems are not just confined to using one of these categories, but you have to use a composition of different categories or skill sets to solve these puzzles. And so every puzzle has an image part to it and a text part to it. And then you have to understand the image in the context of the text and then come up with an algorithm or a mathematical formula for them. And that is where algorithmic reasoning part of the puzzle comes in. And then you have to solve that mathematical formula with respect to the arguments or the parameters that are described in the image or the text, and come up with a solution which you have to select from one of the 5 options. We have so this data set was put out, and then we had a private set of puzzles which are needing similar skills as the public data set for solving these puzzles, but then they were not quite exactly replicated. I mean, the puzzles are different from the puzzles that were in the data set, but then they needed the same set of skills to solve them. We had nearly 20 participants who registered for the workshop for this challenge. And for evaluation, like I said, there were 100 new puzzles, not from the SMART-101 dataset, but then they had the same difficulty level. And it's again similar to what a second grader could solve. And the participants had to submit a Docker image to the submission platform, which was then used to evaluate on these private puzzles. And only one team actually managed to get the submission working and evaluate on our puzzles and the numbers, and that is the team name is YHHY, but I don't know what that stands for, but and they got these accuracies. So baseline is the number that that we would get if we ran our previous method. I mean, the CBPR 2023 paper method on these puzzles, then you get the numbers that are reported on baseline. And the team submitted and their method, and they have some improvements on some of these metrics. I mean, all the metrics, but not significant on metrics. So just to go over the metrics. So accuracy is the frequency with which a method selects a correct answer from the 5 different options. And there are 2 different categories of puzzles. One is just only text. So it might have an image, but then you just need the text to understand what the question or the puzzle is about. And then you just need a large language model, for example, to solve it. You don't necessarily need to interpret the question with respect to the images. Puzzles, which needs both vision and language to be interpreted to come up with the answer. And then we also ran some of these puzzles through ChatGPT to make sure that these puzzles are not so easy for LLMs to solve. And we for those puzzles which the ChatGPT could not solve, we gave it a higher weight, so that if the method comes up and that can solve a puzzle beyond what ChatGPT could do, then it should be weighted higher. So we gave a higher weight, I think a weight of 4 for those hard puzzles, which are those puzzles which ChatGPT could not solve, and lower weight for other puzzles. And then there were voting among ourselves on what is the complexity of the puzzle. And so every puzzle is weighted by some number. And that is this weighted accuracy that you see at the last column. And an interesting thing about these results is that actually for text-related puzzles, this team got a significant boost in performance, like nearly 8% improvement in performance, as you can see in the second column. But on vision and language puzzles, the performance is not significant or significant at all from what we had in the baseline. So there is a lot more to do on the vision and language side of things, is what we gather from this leaderboard. And the award goes to Xingyang Wu, Yang, Shengdong Zhu, Yifang Wu, Qingbo Chen, and Jiefeng Liu. They're from the Nanjing University of Science and Technology and Alibaba International Digital Commerce Group. The method describing this, the method paper describing the approach that they used is going to be on archive shortly. But the winners are going to actually give talk on the SMART-101 challenge. And this is the award sponsored by MERL. And it's a $500 gift card, which will be given to these winners. And now I'll hand over to the winner for their talk, and they are remote. So if they are online, please should unmute yourself.
Hello.
Yeah, we can hear you.
We can hear you. We can hear you. Please share your screen.
I'm ready. Yeah, I'm ready.
Yeah, can you share your slide?
Can you see my screen?
Yeah, it's coming up. Yeah.
Hello, everyone. I'm from Nanjing University of Science and Technology in China. I'm delighted to share our solution.
Wait a minute. Just give me a second.
Okay. I'm delighted to share our solution in the Smart Challenger. This challenger is a multiple choice VQA task, including an imaging question, 5 options, and obtaining the correct answer.
Hold on.
Traditional VQA dataset mainly consists of natural scene images and simple questions that can be answered with basic object recognition and localization skills. However, in this smart challenger, these images are composed of abstract icons, lines, and objects, and the questions require complex logic and arithmetic reasoning skills to answer. Additionally, this computation requires out-of-domain generalization, as the provided test set consists of narrow scene questions. Our solution consists of 4 main components. First, inspired by the official paper, we adopt a divide and conquer approach to categorize the question into 8 types. We utilize the zero-shot capability of
Xiangyu,
large language model.
Well, could you please restart from the beginning? Sorry, you have some audio issue. I apologize.
Pardon? Okay. Can I starting? Hello?
Yes, please go ahead.
Okay. Hello, everyone. I'm delighted to share our solution for this competition. I will present my report in 3 sections: the competition task, method, and results. This challenger is a multiple choice VQA task, inputting an image, question, and 5 options, and outputting the correct answer. Traditional VQA test mainly consists of natural scene images and simple questions that can be answered with basic object recognition and localization skills. However, this challenger, the images are composed of abstract icons, lines, and objects, and the questions require complex logical and arithmetic reasoning skills to answer. Additionally, this computation requires out-of-domain generalization, as the prior test set consists of narrow scene questions. Our solution consists of 4 main components. First, inspired by the official paper, we adopt a divide and conquer approach to categorize the questions into 8 types. We utilize the zero-shot capability of large language model to directly predict the type of each question. Secondly, we automatically construct and train an object detector based on the icon profile dataset. Together with the OCR model, we recognize and localize the objects and test in the input image. Next, we employ the BLIP2 as our base model and added 8 view adapts to the image encoder. This allowed for adaptive extraction of visual features specific to different question types. Lastly, leveraging the powerful imaging understanding and test generation capabilities of BLIP2 to generate the answers. Here is our solution's OMO framework, which includes the original input, information extraction, model input, and model with adapt. The model's original inputs consist of an image, a question, and 5 options. We first extract the 3 information: question type, object class and operations, and the test content and operations. For the question type, we construct a prompt template. There are 8 question types: counting, arithmetic, algebra, special reasoning, measuring, logical, pathfinding. So, question: which type does this question belong to? We then utilize the zero-shot capability of the Llama 2 chat model to directly predict the question type. For object class and operations, we utilize the icon for file dataset by random selecting n archives, randomly assign size, and random placing them on a whiteboard. We construct and train a yellow V7 object detector to recognize and locate objects in the image. For test content and positions, we directly employ the pattern OCR model to recognize and locate text on the image. Once we obtain the question type, object class, and test content, we combine this information with the question to construct a test template as shown in the figure. The test template includes the question type, object class and positions, test content and positions, as well as the question and the 5 options. We then place test template along with the original image into the Paper2 model to pick the final answer. Once we obtain the question type for each question, we add 8 visual adapts to the image encoder of the Paper2 model. These adapts are designed to adaptively extract the visual features specific to different question types. When testing on the private test set, we follow the same setting of first predicting the question type for each question, and then activating the corresponding visual adapt to generate the final answer. On validation set, we achieve the higher accuracy for past and current question types. In addition, we also report the performance of each component, including adapts, OCR, and LOV7. On the validation set, it can be seen that the adapter approach significantly improved the scores. In the end, we achieved an accuracy of 24.13% on the provided data set, which is 5 to 6% improvement compared to the baseline. Okay, that is our solution for this challenger. Thank you very much.
Thank you much, everyone, for attending this workshop. And it's the first workshop on algorithmic reasoning. And I believe algorithmic reasoning is perhaps something that it's like we are trying to go beyond vision and language to something that probably computer vision or machine learning has not really looked. And I think because of this and its and the huge gains that it is bringing in, I think it at higher order reasoning problems where we need to develop algorithms and other things to understand and to inference. And then another aspect of it is generalization beyond the specific problems or data set that that these things are trained on. So we hope that this first workshop is going to be an inspiration for everyone to jump onto this problem of algorithmic reasoning. We have already provided a test bed through our data set for trying some things out, and maybe there will be future data sets that could leverage on this and this idea and have more realistic situations where algorithmic reasoning would be more useful. So to conclude, your feedback is crucial to us to improve future events. We'll continue hosting this workshop series on or relevant events in future on CV, ML, or AI. VLAR. Our proposed next event is going to be hopefully at CVPR 2024. Labs is looking for outstanding researchers as postdocs. So if you are looking for jobs and interested not only in algorithmic reasoning, but in general computer vision and machine learning topics, please reach out to us. And I'd like to thank everyone from the organizing committee perspective for making this a huge success. And we look forward to all of you in the next event that we'll be hosting. Thank you so much.